I'm going to talk about something almost textbook simple today. In fact, I'll talk about the photodissociation of what are perhaps the simplest molecules that there are, the alkali-halide molecules. And from a physicist's point of view, these molecules are interesting because they are essentially few-level systems. There are only one or two or three electronic states of the molecule that are relevant to the dissociation dynamics. And so they provide a kind of textbook look at few-channel spectroscopy, which, of course, Fano was very interested in and which he helped to develop. They're also interesting because the coupling between these few channels is very localized. It's governed basically by a tunneling phenomenon, which is restricted to a very short range of internuclear separation. And the coupling between the channels, unlike atomic spectroscopy, often happens at large distances. And so the parameters that are involved tend to be much more energy dependent than they are in the atomic physics case. In addition, because it's a molecular situation with a large reduced mass of the ions or atoms involved, it can be interpreted very simply semi-classically. So it provides a bridge, if you will, for understanding how quantum defect theory and few-channel physics can be looked at from a semi-classical point of view. And historically, it's played an important role on the experimental side in the subject of coherent control and in the imaging of chemical reactions. This work was initiated by Sean Cornett in his PhD thesis, which was sort of co-directed by Hossein Sadegpour and myself. And Sean really wanted to be here today, but his friends at ITAMP might like to know that last Friday, his wife Fonda gave birth to their first child, son. So if Sean thought he was between a rock and a hard place when he was doing this work, he's probably learning as I speak the real meaning of that term. Also, when we ran into problems, Chris Green was only a phone call away, and he helped us a great deal in understanding the quantum defect theory of this simple system. Because this work was done in large measure when I was at ITAMP on sabbatical, Bala and Brett were here as postdocs at the time, and they got interested in what we were doing, and they helped to develop some wave packet descriptions, time-dependent descriptions of the same phenomena. And when we wanted to move on to a realistic system where experimentalists could easily measure things, we had to do sodium iodide, and that required the input of some very good quantum chemists. And lastly, since we were here at ITAMP, we had the guidance of some people much smarter than us. So the thing that controls alkali-halide spectroscopy, by and large, is one number, and that number is the gap. Okay, and the gap is the difference between the ionization potential of the alkali and the electron affinity of the halogen. And what's listed here from one of Steve Berry's old papers is all the different gap sizes for all the different alkali halides. And we're going to focus on two of them. Lithium fluoride, which is the lightest system, has the smallest relativistic spin orbit effects, and so it's simplest in many respects. And sodium iodide, which is heavier and has the additional complexity of a large spin orbit interaction. Both of them have about 2 electron volt gaps. So let's start with lithium fluoride. And to a large extent, lithium fluoride is almost a perfect dipole. It's the physicist. It's the closest a physicist has to a real dipole in the universe. The ground state Born-Oppenheimer potential curve looks like figure A here. And if you just take that, where's my mouse? If you just take this curve and you subtract the Coulomb interaction of the lithium plus and the fluorine minus, that is to say 1 over R, then you get curve B. And curve B, you see, has this slight attraction, which is just due to the polarizability of the 2 ions. And so then if you subtract the polarizability of the 2 ions, you get curve C. And curve C is just the exchange repulsion of the 2 closed shell systems. So it's really a very simple system governed by simple forces that are easy to understand. Fortunately, that's not the only state of lithium fluoride. There's also excited electronic states, which are, I'll refer to as covalent states. They're basically repulsive, and they correspond to neutral configurations of the two atoms. So the correlation in the alkali halides is extremely simple. If the electron is arranged so that there's an ion pair, okay, if you're in the ground electronic state, then you have an ion pair, and the ion pair interacts by Coulomb interactions. If you're neutral, then you repel, and basically that's all that's involved in the correlation of the two systems. In particular, if we consider photoabsorption from the ground state down here up into these excited electronic states, basically what happens is that the electron hops from one center to the other as it absorbs the photon, neutralizes the two atoms, which realize it, and then just fly apart. And that's all that's really involved in the photodissociation. In particular, if you do the photoabsorption so that you align the polarization axis with the axis of the molecule, then you make a sigma to sigma transition, and you can understand the dynamics simply in terms of these two channels. So we have a simple model of lithium fluoride dissociation, which considers only two electronic states, and in which one undergoes a transition like this. And so it's a very simple dynamics. Of course, the two states are coupled to one another, and there's a small avoided crossing there that's associated with the tunneling of the electron between the two centers. And so there's a non-adiabatic coupling matrix element between the two channels that peaks at about 13 atomic units. The Frank-Condon photoabsorption transition goes up to here and comes out here. So there's an energy region here, an energy window in which you're going to get dissociation. And the Landau-Zener probability for going through this crossing diabatically is about 80% in the Frank-Condon window. So if the atoms start to dissociate as neutral atoms, 80% of the time they make it out. And 20% of the time they switch after 13 atomic units and become ions again, and that's all that's really happening. So that's the situation, and now you just have to solve Schrodinger's equation, and it's easy to do. And what you find when you solve Schrodinger's equation is a very amusing-looking Rydberg series. It's not the kind of Rydberg series you're perhaps used to seeing in atomic spectroscopy. This is a vibrational Rydberg series. This is two heavy ions interacting by Coulomb interactions and vibrating in a Rydberg series. And you see several hundred states of this Rydberg series here. It may look like a very complicated spectrum, but it is a single Rydberg series. And if you blow up a little portion of it here, it looks like this. And so you see it's just one Rydberg state after the other. But what's unusual about it, or was to us as atomic spectroscopists, was that the Fano line shape is changing in a periodic fashion as you move through this spectrum. You see here you have Fano Q parameters of one sign, and then Q parameters of the opposite sign, and then that repeats as you go through the spectrum, and it's that repetition that gives rise to the intermediate energy scale that you see there. You see a broad Frank-Condon energy scale, you see a sharp Rydberg energy scale, but you see an intermediate energy scale having to do with the modulation of the spectrum. And it's that intermediate energy scale which is correlated to the 13 atomic unit size of the avoided crossing, and that's what we're talking about. Now, the broad feature that you see underlying that spectrum really comes from these window resonances and from the tops of these window resonances, and they're forming that background, and that will change when we go to sodium iodide later on. So here we have a situation in which, again, on a small energy scale, the Fano Q parameter is actually changing periodically as one wanders through the spectrum. And Felix Smith's delay time is shown here. And what you can see is that there are some extremely long-lived resonances. In fact, you can't see how long they live on this scale. They live for hundreds of picoseconds, and so that the lifetime of these resonances becomes comparable to the radiative lifetimes. So they no longer predissociate. So there's some very sharp resonances that occur in this spectrum. And And here we see the QDT parameters, the two dashed lines, so the two eigenquantum defects in this two-channel model, and you see that they're oscillating through the spectrum. They're not slowly varying energy-dependent parameters. The solid line is just the full phase shift, eigenphase shift. In atomic spectroscopy, we're used to seeing Rydberg states that all look alike, auto-ionizing resonances that all have the same Q parameter as one wanders through the spectrum. Occasionally, you'll get a Q reversal as one wanders through the spectrum, and that's usually due to the existence of some interloping level, some other state comes in. But in this spectrum, we have a Q reversal happening without an interloper, and that was new to us because we hadn't seen it before. The other thing that was amusing about this simple two-channel lithium fluoride is that all of the, 40 years after Fano published his 1961 paper, there's been a lot of things published about two-channel spectra and a lot of parameterizations of two-channel spectra. And the fact is, we tried to fit a Q parameter to that spectrum using all the different variations that we could find, and none of them worked because this is a situation in which the coupling happens at large distances. And so we had to develop a formula for Q, which we haven't seen anywhere else in the literature before. And this is a Q that seems to work for all two-channel spectra, providing it's really only two channels in the system. And Q is directly expressed here in terms of the difference of the two quantum defects, eigenquantum defects, and the mixing angle, which is essentially the eigenvector of the short-range K matrix of the system. So this little formula here seems to work beautifully, and it fits all the spectrum, and it relates the Q parameter to the K matrix of the system and to the dipole matrix elements. So yes.
Or have you got us?
No, you can. No, we derived it, but we had, but people have derived other formulas for Q and how it varies with energy, and we couldn't get those to fit. This one fits. Okay, this seems to be a generically valid formula for the Q parameter. Of course, this is an energy-dependent function, and what you have to do is evaluate this function at the peaks of Felix-Smith's delay time in order to find the Q value at the resonance position. And that's the way we do it now. So that's the way it works. Okay. Now, I wanted to go back. How do you go backwards? Just back arrow. There we go. I'm not very good at PowerPoint. The other thing that came out about this is that so the Q, what was really controlling the lithium fluoride spectrum was the mixing angle, not the quantum defects. And you can see that here on the scale of the whole Frank-Condon window. You see that whenever the mixing angle goes to 0 here, okay, that's what's modulating the entire lithium fluoride spectrum. And so what's happening here is really very simple. If you have a dense spectrum of Rydberg levels, if one of those Rydberg levels happens to lie at an energy that corresponds to a 0 of the mixing angle, the channels are essentially decoupled, and that state just lives essentially forever, or at least for a very long time. And so it's this mixing angle that's governing the nature of the spectrum. And the other thing that's amusing about this is that the smooth energy parameters are not the K matrix parameters because the coupling is at large distances. It's actually the semi-classical parameters that are smoothly varying in this spectrum. It's the Landau-Zener parameters that are smoothly varying. And there's a very simple relationship between the K matrix parameters and the semi-classical parameters in this case. Here, this picture is showing how the transition probability. So the way you think about this, you start with the two ions, and they come in and they scatter, and you ask for the probability that they come out as neutrals, okay? And you're seeing how that varies as a function of energy in the spectrum. The solid line gives the quantum defect theory calculation, and the diamonds here show just the simple Landau-Zener theory. And you can see how beautifully they agree with one another in this spectroscopy. Now, having seen this, we wanted to look then at the same thing from a time-dependent point of view and see how this two-channel spectroscopy develops in the time domain. And so I'm going to show you a little movie here. This brings in the frame transformation idea. The short-range physics is best described here in the adiabatic representation, where the photoabsorption takes place. The adiabatic channels are the best description, whereas the avoided crossing region, because the Landau-Zener probability was 80%, is much better described in a diabatic representation. And so you have to put both pictures together to really understand the wave packet dynamics. This first wave movie is going to show you the adiabatic representation, which controls the initial photoexcitation process. And let's see if I can get it to work. Oh, well, it wants to start in the middle, which is not a good place to start. So hold on a second here. I have to go here. Okay, here we go. And now I start from there. And here we are. So now you see that initially the wave packet comes out on the upper state. The two neutral atoms are flying apart. And when it gets to the crossing radius, which is about here, all of a sudden 80% of it gets over here, which is now the neutral part, flying apart. And about 20% of it got caught. Now they're ions, and the ions are moving apart, but they don't have enough energy to separate. So the ion part is going to turn around and come back. Okay? And so what we've got here in the upper adiabatic channel is a Rydberg wave packet that's moving out, spreading, turning around, and coming back, and scattering again at short distances. Now, to really understand the movie, you have to look better in the diabatic picture. So here's a movie in the diabatic representation, and you can see that it's a little awkward. It comes out in both channels here because it's not a good description at short distances. But now this one is the ionic channel. And you see this Rydberg wave packet turning around and coming back, and 13 atomic units is about here where the crossing is, and it starts feeding into the other diabatic state, and you get a standing wave in that other diabatic state. And what it does is it starts to shake the garden hose, and you can sort of see the garden hose shaking out there as the neutrals fly apart. You can also see that there's a strange dispersion because the wavelength is actually longer at short distances than it is at large distances there. And understanding all of the details of that turned out to be a very complicated thing. The time-dependent dynamics is much more complicated to understand in detail than the time-independent dynamics. I remember asking Hugo about wave packet dynamics when I was a student, and he said, "Oh yes, Fourier analysis," and then he walked away, and that's all he wanted to say. So yes.
So did you ever look at it in case space? If you look in case space, you will see that your picture that you want to recover is there.
Oh, I'm sure. Yeah, absolutely. No, but have we looked at it in K-space? No, we haven't. One could do that. Of course. That's right. No, that's right. Yeah, that's right. Oops, I went too fast. That's all right. Let's see. This is some stills of the wave packet dynamics, the diabatic wave packet dynamics, and I just wanted to point out this thing I was talking about. The wavelength here is much longer than it is out here, and you might think that that's just because the neutral atoms are accelerating as they fly apart, but beyond 20 atomic units, the potential is completely flat, and so there should be no change in the wavelength as you go on further. This happens because what the Rydberg wave packet is spreading out, and what happens is that the high frequency components, the more deeply bound parts of that, come back quickest. And so it's the highest frequency stuff that's coming back in the Rydberg wave packet first, and then the lower frequency stuff comes back later, and that's what's changing the wavelength in this picture as you go on. And then you can see recurrences of the wave packets happen down here, and that modulates the thing. The high frequency components come back again, and they modulate this thing. And the wave packet dynamics gets quite complicated and amusing. What was amazing to me, was just how well solving the time-dependent Schrodinger equation works, even though it's much more difficult to interpret. Here, if you just wait long enough, you get the spectrum as you expected, and you can sort of see it emerging from the wave packet dynamics. And this shows a detailed comparison of the time-dependent wave packet dynamics with the time-independent calculation. And you can see how well they agree. How much time do I have, John? Okay. When you go to a more realistic, another system in which the experiments are actually willing to put the stuff in their apparatus, sodium iodide, things get much more complicated, or at least a little bit more complicated because of spin-orbit interaction. Now, this is a calculation of the Born-Oppenheimer potential curves without the spin-orbit interaction included, and you see it looks rather similar to lithium fluoride. When the photoabsorption takes place now we go basically from this singlet sigma state here to the singlet sigma state up there, at least if you excite along the axis of the molecule. And it's that transition that's going to govern the behavior of the system at short distances. However, at large distances, it's the spin-orbit interaction which takes over. So if we then include the spin-orbit interaction, this happens, and you see those states get split, okay, because it's spin-orbit. And so now the photoabsorption is still taking place at short distances where the spin-orbit isn't quite as important. But now the dissociation is going to take place in this context. The difficult part was trying to figure out how to diabetize this system in a reasonable way, and I won't talk about it, but we did. And basically, you can reduce it to a three-state description in which there's basically the ionic state crossing two other covalent states. Most of the photoabsorption is going to take place sort of in the window between these two, okay? But what's interesting is that even though that third channel is basically closed, you can't neglect it from the photodissociation dynamics because of the fact that you're doing the photoabsorption at short distances where really the spin-orbit interaction is not quite so strong. So this is an example of a sort of a textbook example of Fano's idea of the frame transformation with different descriptions appropriate to different regions of space. Child realized this long before we did, and he had to introduce a kind of basis set that goes from the adiabatic to the diabatic as you go from one region to the other in order to describe the details of the sodium iodide spectrum. So you go ahead and run it again, and you find a similar kind of spectrum here. This is wavelength, so it's inverse to the figures I was showing before. The Frank-Condon window is down here. Then if you look up above the second state here, the reason you don't see any structure in that lump is basically because you haven't run the simulation long enough to resolve the wave packets that are moving out much farther out in the ion potential. And so you have to run it much farther to see the structure in that upper Frank-Condon region. If you actually look in a narrow window now to see what the resonances look like in sodium iodide, you see something quite different. You see there's no window resonances in sodium iodide. You see, they all go to, that Frank-Condon envelope that was formed by the window resonances in lithium fluoride is now missing. And that's just due to this frame transformation notion that there's three channels really involved at short distances. I'm almost done, John. Okay. And if you actually look at the wave packet dynamics and calculate the survival probability of the ionic component, then you see these recurrences in the spectra, and that is, of course, what Zawale focused on and measured so nicely with his time-dependent pump probe spectroscopy of sodium iodide. And so you see variations of the ionic component with time, which are quite comparable to those we obtain in our calculations. So to summarize, alkali-halide photodissociation studied in the frequency domain turned out to be textbook simple in many respects, and yet involved some things that we didn't expect. Some rich spectroscopy, which was greatly facilitated by the kinds of analysis which Ugo Fano pioneered for several decades. And lithium fluoride in particular was a simple two-state model of energy dependence in spectra, while sodium iodide illustrated the importance of frame transformation contexts, frame transformation ideas in the three-channel context. And so with that, I'll thank you for your attention.
Any questions?